Hi, software developers out there. As software developers, we pretty often work without any knowledge about the hardware. And some hardware guys are probably wondering about that, but yes, on some parts we have to know. Let's today talk about caches, cache coherency, cache lines, and the effect on software and how we can really change the software to be efficient on that case. Okay, let's dive into that. Do you, as software developer, know your partner, the hardware? You should, at least to some degree, where software meets hardware or caches and shared state concurrency. Here's a big picture with two combined. We have the software view on top and we have the hardware view on the bottom. The software exists with threads, which is an execution context, which usually maps the cores by the OS. We have data, pretty often in the form of objects. And those objects and data get mapped to a programmer's memory model, which is a linear address space, and we get address and can put data into there. Doesn't matter if it's virtual or real physical address. In the end, it's physical address, and the data lives in the DRAM physically. But the DRAM is slow, so usually those cores today add some caches. Okay, let's start with the cores. We have core, in this example, 1, 2, and this should be 3 and 4. There's a closely attached level 1 cache, usually split in data and instruction. We talk about data here only. There's a level 2 cache. It's a little slower, a little bigger. And then there's a level 3 cache. Again, it's even slower, but it usually combines the cores. Sometimes we have even a level 4 cache, for example embedded DRAM. And then we have the DRAM as already tagged. That's exactly where the data is really physically stored. By the way, cache means hiding place. That has a reason. Because the programmer's memory model can't see any of those caches. It does only see the DRAM. So this one and this one maps, but this one is transparent. We don't see it. But there is a lot of complexity in there. Why adding so much complexity? Well, the major reason is that the programmer doesn't want to change the logical memory model he has in mind. And the hardware says, okay, I will solve that for you, at least partly. So from the software world, we don't want to cope up with all those different cache levels we have and the different cache strategies we have. Sometimes there's one L1 cache, no L2 cache. Sometimes there's L1 to L4 cache. We don't want to program for all that. Okay, again, why do we have the caches? Because CPUs need random access memory, but DRAM is really bad on that. DRAM is cheap and has a higher throughput, but only in streaming mode. Caches are really transparently added to solve that problem. Without caches, high-speed cores would essentially only wait for slow main RAM. They will be fast waiting, so we need them. But we have to understand them. Okay, let's take a look to the programmer's world again. We have the programmer's memory model. If we have a class, and this class is instantiated means we make it real, put it into memory. We would probably end up having some address here, starting address. The first 4 bytes will be held to apples. No, not the apples, the counter for the apples. We can't store apples here. And the second one will be peaches. Well, currently we don't care about them. The class itself has methods as well. This one is incrementing apples without any mutex log and all that stuff. I know that's necessary later on, but it's not in focus. Those are called from out a thread, because a thread is the programmer's execution context. This thread has to be put on a core because it has to run in a physics. the core is, from the hardware point of view, one of the cores we have. Okay, now the apples get incremented and we'll see what happens here. Let's take a small look into the physical world again. Since here we only have the programmer's memory model with addresses, we have to take a closer look what's going on here. That's the same as we have seen before. The apple counter exists in a DRAM, of course, but there's a couple layers in between before it essentially gets executed by a core. This should probably be more a core. Okay, so let's now start counting apples on one core. So we start with a load instruction and we want to get something into that register, so we issue a load instruction from the core which goes down to the L1 cache. Oops, there is nothing, so it goes down to the L2 cache, to the L3 cache, and finally there will be something on the DRAM. So let's say we start with a 15. So the 15 will be pushed up through all the caches, which itself takes time, and gets loaded to the core. So we have that 15 here now. Now, since we're counting, we're making out of the 15 a 16, which gets stored into the L1 cache as well, because that's acting as our memory now. So now it depends on what cache strategy we have. There is that write through cache, which means we're writing through all the caches down to the DRAM and put the 16 down into the DRAM, but you can assume that this one is definitely time consuming. We would save some time for the next read though, because we still have it in the L1 cache, so the read will not be necessary. But even the write is something which will take time and of course current. So the normal strategy nowadays is that we keep it in the L1 cache, it's called the write back cache. It will be done later, writing it back to DRAM. So we load it for the next instruction, we load it and say you get a 16, which gets, as we increment it, down to a 17, which gets stored. So we have a 17 now here. These are kind of two instructions. And if that's the end of the counting, at some point in time, this 17 will get pushed down to the cache strategy, to the cache lines, and get down to the DRAM. So that's what happened on one core. Okay, we have seen one thread on one core. Now let's see two threads on one core. Well, there's not much to say from the hardware point of view, since we are running on the same core. The caches are the same. So that's just a little bit of scheduler thing, that there's always this interrupt switches from one thread to another. So from our point of view currently it doesn't make any differences. But what happens if we do the same with two threads and two cores? Do you notice the difference here? From the programmer's point of view, there's no difference, since mapping to the core is something which is done by the OS. But all of a sudden, if we go from this one, that the threads are mapped on one core, to this one, that the threads are mapped to two cores, we have a big change. Let's see what's going on with this one on the physical world. Again, with two threads on one core, there's no change. But with two threads and two cores, there is a significant change in hardware paths, and the data flow is different. Let's see what's going on in such a case. Okay, so now let's start counting apples with two cores. First of all, about the picture, we have two separate cores. Each of them had a L1 cache and an L2 cache, and They share a common L3 cache. I just print it like that so I can write the numbers in here to show that they belong to both. And that's the same for the DRAM. Okay, so let's start the same with, we have that 15 which is currently stored in DRAM, and we start with the core 1 and say, okay, from the timeline we want to load into the register number 15. So it goes all the way down, it goes down to that cache. As we have seen before, it goes down into here. The 15 gets pulled out of the DRAM and put into L3 one, still a shared cache. And then we got the 15 here up in the L2 cache, so one from the core 1. So we got the 15 here. The same applies here, the same applies here, and all of a sudden we have the 15 here. Since we're counting, this will get a 16. The 16 will get pushed down to the L1 cache. So we have the 16 here. So as we have seen before, if we would now start counting 17 on core 1, we will just do it here. But what happens now? Let's say we have a thread or a core switch. So the next counting step is just done on this side. So what we need to do is we want to get the register filled with that number of the apple counter. So obviously, since we have no cache line for that, we go down, and obviously we find something here. Then we pull that up, put that 15, and we have already seen that there is a problem, since we have a 15 here, but before there was already generated a 16. So we will create a problem here. So what can be done? There's two possibilities for a core. Either all of them get written through, as we have seen before. If we always write through, then we probably don't have that problem, at least. But that's not very efficient. So what cores can do, they can communicate between the caches. Usually that's done on the L2 cache. So this one gets written down automatically to the L2 cache, and then we have here something which is called cache snoop protocol. That means when we go down here, this one will ask this one if there is this address already in his cache, and if that's the case, they will transfer the data, or they will agree that they will be put down into L3 cache. So we will delete this one and write the 16 down, which has to be done probably as well. But what we can see from all those actions, see, we started here. We want to get this number, which is not here, because it's cached on the other side of the core. We have to go down to this one. This guy has to talk to this guy. And this one has to be written down and transferred to the other side. So there's a lot of actions going on, which takes, again, time, since those are usually slower because they are bigger. So there's a couple of cycles we add here, just because we are accessing the same memory here from the core 2 as we have used in the core 1. So the problem is we have loaded something in that cache here, which is the same as we have here. They are realizing the same thing. They're caching the same thing. And because that's the case, there's a lot of effort here going on to synchronize them, which is time consuming and power consuming. Okay, let's go away. If we just get down, we have that cache snoop protocol. We got that 16 down here. That 16 gets transferred over to the L2 cache, probably into the L3 cache as well. And then this one is solved, since now we really have the 16. And we got it up here, and we got it up here. So we ended up having 16 here, which we obviously count now and put it down to the L1 cache. So now we have the situation again. This one and this one is not the same anymore. So on this write, this has to be invalidated, or it's the other way, as I said, or pushed right through. So it is now the case. We have that case before. In the first case we had the case that this one is not there at all. It was just filled. But now we have the case that both addresses are stored in both L1 caches. So in that case we write the 17. This will get pushed over to the other side. And again, just because we might need that value on the other side, we are doing a lot of actions. Again, time and power. Okay, we have seen how incrementing apples with 2 threads in one core is working. We have seen the same on 2 threads and 2 cores, but still with apples only. But you may have wondered why there is peaches in the class fruits as well. There is for a reason. What happens if we increment apples in 1 thread on 1 core and increment the peaches on the 2nd thread in the 2nd core? Well, that should not be any problem, because we are not running in the same problem we have seen before. We are working on different memory areas. Well, not really. Let's take a closer look. And now we're talking about the so-called cache lines. Since caches are not caching 1 byte or 1 word, they're caching full cache lines. And the number of bytes in a cache line varies on the type of cache and the type of a CPU. Sometimes it's 12 bytes, sometimes it's 256 bytes, or probably even longer. First, that's something we don't know, which is hard to deal with because we have to deal with. But let's see what's happened. Okay, so what we will see is that the physical memory model, which is the same as the programmer's memory model, if we want to do something on the apples, they will get loaded into the cache. But of course, they will not only be loaded as this one, they will load a couple bytes or words here as well. So in this case, it's most likely that the apples and the peaches are just side by side in the same cache line. So now they are loaded. If we increment the apples, and we have the same on a 2nd core with peaches, the only thing the cache organization does know and is managing is it changed or not, but they don't do it on a byte level, they do it on a cache line level. So now we have the situation that in the 1 core apples are incremented, and in the 2nd core peaches are incremented. So, but they are treated as one memory. We have exactly the same situation as we have had before with apples. And now remember that I have said the problem we have is independent of mutexes. This is not a mutex problem at all, because loading apples, increment and save and do the same on the other thread is really a problem if you do it without mutexes. But you can safely do this with apples and peaches on 2 different threads without mutexes. But this problem we have explained before is still valid. So what can we do in order to avoid that? Well, one possibility is that we put the pitches in the same class, far away, and hope that we get in the other cache line. If we manage to get in the other cache line, then we don't have any problem at all anymore. Well, if we make small classes, it's really hard to do that. So the way better solution might probably be to build classes which no two threads are using them, or at least threads which are never scheduled on different cores, which is hard to manage, by the way. Okay, let's do a small test application to see the effect, because I think it's important to see the real effect. That's not theory, that's real life. Okay, let's go into that. So we're writing an application where we're emulating exactly this one. We have the first situation where two variables are really close to each other, and we're running on two cores. Well, create two threads and hope they're scheduled on two cores, and we prove if that's happened. And then we essentially add some dummy space between the apples and the peaches and increase that space to, well, probably 4K, we will see. And then do the exact same test again. Think about what would be your expectation now.
The application is simple. It fits on one screen with the main, which creates two threads, and within each thread the big data array will be accessed on a location which is defined by distance. That's all it is. I guess you can press pause button and get through that.
Okay, let's test. I've written a small makefile which does the job. Let's see what we're calling. We're calling the Unix time command, which is measuring the time it takes for the next command. Then we use the task set to specify the next process to run on those two cores, the two given cores, 0 and 2. Then the application we have seen before, and the distance between the two variables which are counted by the two threads. So we see thread 0 runs on core 0, thread 1 runs on core 2, and we have those addresses they are working on. With a 4 KB distance, we got almost 8 seconds user time. Now let's see what happens with a 16 bytes distance. We do exactly the same, with the exception that thread 0 runs on the address 00 and the other one on 10, so it's only 16 bytes distance of the two, so there is a big chance that they both go into the same cache line. Now we get almost 23 seconds. Okay, let's do the same, just running on one core. It's the same, 4 KB and 16 bytes. The numbers are almost equal, so there's no big change, of course, because we don't have that problem. Okay, let's see how the system is really designed. We got, as far as I know, it's a very old Xenon machine. It has 2 sockets, and on both sockets they are 4 cores. So we have been using this one and this one before. So we're running on one socket and we're not touching the other socket. This one is not very... So what can we do to avoid those problems at least as much as possible? We have to work in parallel somehow, because we're working on one problem and we're working on different cores, so we have to interact to a certain degree. The question is, how often do we interact? Let's see that on the example. So how often do we have to interact in this game? And how often do we have to interact in this board? That's a major difference. That's the difference between parallelism here and concurrency here. Concurrency means we all compete on the ball. It's kind of a single state. And this one has to be done very often. While this one, we can work for a very long time, totally independent with the maximum speed we have. So those two pitches are essentially introduced by Pablo Capra from Intel, and I think it's a very good idea which shows what situations we face. Concurrency, which is a bad situation in the software. Parallelism, which would be a perfect situation for the underlying hardware. So our goal in software is to get as much as possible of this scenario and as less as possible as this. We can't put that to zero because we have to work on one common problem. And those guys essentially work on their totally own. The only common thing is the time. What abilities do we have to overcome that problem? Well, simply speaking, we have to make sure that the data we are accessing from different threads are really not closely in the physical memory. That means they don't fit in a cache line. But there's so many other things we have to follow on the software development anyhow. So the better solution would be that we in general move away from the idea that the control path is something we don't fully have under control. That's why I really go towards actor patterns. So the data we are working with are we are working with one thread. At least the data we are working on all the time. Of course we have to communicate, but that's exactly what the actor pattern is about. We are sending messages. We are sending tasks not in the form of threads. It's really a task as we know in real life. And we treat computer applications more like human beings. That's exactly the actor pattern. Since we have objects in the object-oriented world, but they are passive. Well, that's the real thing in the reality as well. Move to an active part, being a subject, which is able to have a control path, that's our action, and the data itself. And we are only communicating with each other. That's the only possible, well, it's not the only possible way, but that seems to be a very good solution for multi-core applications in the future. There is a couple more things. We can go a little bit easier to say we use communication between threads, which is the actor essentially using as well. We can use things like Occam has done, which is now part of Go as well, to use channels. There's different ways, but the only very important thing is that there are some things we have to take care in the object-oriented world and move to the next step and think about the hardware as well. And that's the only possibility to get in a low power scenario as well, because what we have seen before is not only a timing problem, it's even more a power problem, because getting all those logic in place and all those switches active and all those communication within a chip happen takes and consumes power as well. Okay, how can you solve that? Well, first of all, just make bigger tasks. If there's bigger tasks, you don't have to communicate between them very often. And that means reduce dependencies between them. Well, by the way, it is a software quality in general as well, because that makes software manageable. Oh, about management, yes, take management patterns to solve that. Within the management, you have to give people tasks where they can do the task mostly on their own and don't have to interact between them, because otherwise you will get slower. And that leads to a pattern which is called the actor pattern, which I really like too. Actor pattern means we're going from the object-oriented world to kind of the subject-oriented world. In the object-oriented world, somebody on the control path is doing something with objects, whereas in the actor pattern, in the subject-oriented programming world, we have tasks which take control path, they act, but they have the data, the objects, in their container as well. That makes it very efficient to solve that problem. Well, actor pattern means there is a communication between two actors, two subjects. Well, as it is in real world. That's why we can use management patterns, by the way. And now we're only communicating between each other. That leads to another thing. Copying is not always bad in software. Pointers and references sometimes have really bad effects, as we have seen, because they are working on the same shared states and the same variables. Another thing, rather than using actor patterns, is using channels, like in Go or similar languages. Very old is the OCaml language, which I still like. Even event-based programming may help, kind of. It's not that it helps to put the tasks on different cores, but at least on one core, it avoids that the US scheduler is scheduling threads to different cores, which we probably don't want to. Well, essentially it all leads to you have to be aware of the data in the control flow and take care about both. As I've said, it's happening in the actor pattern because you're having the control path in the actor because it's an active object. And you have the data, well, sits in that object, all in one container. But it doesn't really matter if you use the actor pattern or use plain C or whatsoever. The most important thing is that you really take care of the control flow and the data flow and really know what's going on. Okay, that's all I have to say now. Thanks for watching and bye.